Hey guys, here we go with our unit on gas laws. So here's some of the things that we're going to talk about, factors affecting gas pressure, and describing the relationship between temperature, pressure, volume, and we'll do a whole bunch of calculations. So first, the properties of gases. There's a few things to keep in mind here. I'm not going to read this whole slide to you, but you should pause this and take a look at it. This is why gases behave the way they do. First of all, you should realize that gases are compressible. Compressibility is a measure of how much volume decreases under pressure. So because gas molecules are so far apart, there isn't much space between them. This means that they can be compressed. Liquids and solids cannot be compressed. You can't take a pencil and then compress it down into a smaller pencil. You're just going to end up breaking it. Liquids can slightly be compressed, but not so much. This is why you have liquids in your brake. You've heard of brake fluid. Liquids are pushed through your system to activate your brakes, and because they don't really compress much, this can happen. You can't do it with gases. Imagine you had gases in your gas line and you pressed on the brake. The gases are just going to compress and never make your brakes activated. So here's a picture of a cylinder. You've all seen gas cylinders. Inside that cylinder, they force gas molecules in there, and then they increase the pressure. Anytime anything's under pressure, it's a compressed gas. You can squeeze a lot of gas inside that tank, much more than its normal volume allows, because you can compress it in there. This is called the kinetic molecular theory. This is how gases behave. So just take a look at these. Gas particles are in always random motion. They continue in a straight line until they collide with something. We can assume that gases have no volume. They do, but it's very negligible. So we're going to pretend that they don't have any volume compared to the space between them. There's no molecular forces at work. That means there's no interactions between the gas molecules. They're not chemically reacting with each other. They're just kind of bouncing off each other. Gas pressure is due to molecules colliding with the walls of a container. That's what gas pressure is. This tank over here, it's measuring the collisions of all the gas. Imagine all the gas particles are bouncing around in here, and how many times the particles hit the walls of the cylinder is measured by a gas pressure gauge. The kinetic energy of a gas is measured in Kelvin. Very important. We're always going to be talking about Kelvin temperature here. All gas problems have to be done in Kelvin. So individual gas molecules have different speeds. It's related to what their temperature is. We'll talk more about the relationship later, but you just have to realize that temperature is related to the energy of gas particles. All gases at a given temperature have the same kinetic energy. So, everything in your room right now is the same temperature. It's all, room temperature, whatever you have your house set at right now, 70 degrees or so. So everything in your house right now is at 70 degrees, meaning that all the particles in there have the same kinetic energy. Some may be moving faster than others, but the energy is the same because of number 8. Lighter gas molecules move faster than heavier ones. So, just like a sports car is faster than a truck, a small gas molecule such as something like helium would move faster than something like xenon. So take a look at these. This is why gases do what they do. So let's take a look at the factors that affect gas pressure. So there's 4 different factors. We have pressure. The volume of a container has to do with the pressure. The temperature, as I said before, the hotter something is, the faster the gas molecules are moving. And moles, and the number of gas particles. the more gas particles you have inside a container, the more pressure there's going to be. So there's a relationship between all these four things, and that's what our calculations are going to be about. You should be aware of the units here, so you could recognize when you see a number. If you see a number that's 100 atm, that means that's the pressure. There's a bunch of different pressure units. This atm is atmospheres, kPa is kilopascals, mmHg is millimeters of mercury. They'll use this on the Weather Channel a lot to talk about weather pressure. And torr is one that we used often when I worked in the gas business. Volume should always be in liters. It doesn't have to be until we get to the ideal gas law, then it must absolutely be in liters, but typically they're in liters, maybe milliliters. Temperature always has to be in Kelvin. There's no two ways about it. The conversion for this, if you get a question that's in Celsius, you have to do a conversion. So Kelvin equals Celsius plus 273. So if you get a question that's in Celsius, say you get a question that's 10 degrees Celsius, you have to convert it to Kelvin. So you're just adding 273. This would be 283 Kelvin. All right, so you'll see that sometimes. Don't mess. Be aware of that. You always have to be in Kelvin. This is the formula for converting it from Celsius to Kelvin. And moles, the symbol for moles is just N. We'll see that in the ideal gas law. So let's talk about the three gas laws. The first one is called Boyles Law. These are people. Boyles did this years ago. And this relates pressure and volume. Pressure and volume. So here's a little chart that shows the relationship between pressure and volume. If you hold the temperature constant, the volume of the gas varies inversely with the pressure, meaning as one goes down, the other goes up. As the volume decreases, the pressure increases. This is what this chart is showing us here. Here's a fun little simulation. You guys will play with this in one of your assignments for the week. So let's see what happens. We're talking about Boyle's Law. Let's pump some gas molecules in here. All right, we'll give them a chance to float around. Notice we have a couple settings here. This is our temperature. It's in Kelvin. Okay, we don't ever do things in Celsius, but you could see this is about room temperature, a little bit warmer, 27, so that's about 300 Kelvin. So roughly 300 degrees, like 298 really is like room temperature. Here's the pressure. You could do, this is set for ATM or kPa. We'll just leave it in ATM. So since we're doing Boyle's Law, we're going to hold the temperature constant. I'm going to press this so it doesn't change the temperature. So we're relating pressure and volume. So the pressure here is about 19. It's fluctuating a little bit. Let's see what happens when we make the box bigger. We increase the volume. What do you suppose is going to happen to this pressure if we make this box bigger? Let's check it out. Let's make it bigger. Not quite double, maybe a quarter of the way bigger. We were at 18.8. Boom, the pressure dropped. That makes sense because there's more room inside the box for these atoms, molecules to move around. They have more room, so there's going to be less collisions. Let's make the volume smaller. Let's see what happens to the pressure. We're about 12. We decreased it a whole bunch. Boom, the pressure increases. So play around with this when you have this assignment, and you can see it's really kind of obvious. It's very logical, gas laws. This is usually one of the easiest units of the whole entire year. People usually like gas laws because, like I said, it's kind of logical. All right, pressure decreases as the volume increases. As one goes up, the other goes down. That's what inverse means. The next gas law is called Charles' Law. This one relates volume and temperature. V1 over T1 equals V2 over T2. This time at constant pressure. Notice pressure is not in this equation, so we're holding it constant. This is just about volume and temperature. the volume of a gas varies proportionally with the temperature. That means as the temperature increases, the volume is going to increase. And that's what is shown by this graph. Remember, the first graph went the other way. It's going down. As you increase the volume, the pressure is going down. It's inversely proportional. Charles' law is proportional. As one goes up, the other goes up. Let's take a look at our simulation again. We pumped in some gas molecules, and this time we're interested in volume and temperature. So I'm going to hold pressure constant. So let's see what happens if we increase the temperature. We're at 300 K. Look at the pressure here, almost 17 atm. Let's increase the heat. What do you think is going to happen to the volume of this box if we make these molecules hotter? The box gets bigger. Notice that the molecules are moving faster. This is what happens when you increase the kinetic energy by heating it of the molecules. Heat it up more. Oh, sorry, look at the temperature. Temperature's going down. Temperature's going down as we decrease the volume. Oops, I went too far. So you can see how temperature and volume are related. As one goes up, the other goes up. One goes down, the other goes down. That means it's proportional. So let's take a look at the third gas law. This is Gay-Lussac's law. This relates pressure and temperature. P is over T's. P1 over T1 equals P2 over T2. We'll do these calculations in a minute. So notice there's no volume here. So at constant volume, meaning we're holding the volume constant, the pressure of a gas varies proportionally with the temperature. That means as the pressure increases, the temperature increases, shown by this graph here. So they all increase proportionally with each other except for the first one, Boyles Law, which the line goes down. Let's take a look at Gay-Lussac's law, pressure and temperature. So we're going to hold volume constant this time because that's what Gay-Lussac's law is about. And let's look at the volume. Let's look at the pressure and the temperature on how they're related. So let's increase the temperature. What do you suppose is going to happen to the pressure? We're going to increase the temperature. It's going to make these guys move faster. Let's watch that pressure. There we go. Pressure's going up. Look at the temperature. 5, 6, 700 Kelvin. Pressure went up to about 40. Let's cool it down. Temperature's going down, down, down. Look at the pressure. Pressure's dropping. This means they're proportional. As one goes down, the other goes down. Let's see what happens if we can get it really, really cold. So remember, 0 Kelvin is absolute zero. Theoretically, that's when the motion of atoms stops. There is no negative number for Kelvin. There are no negative numbers for Kelvin. This is one of the reasons why we use them in gas laws. We can't have negative numbers, so we use the Kelvin scale. Here we go. We're down to 1 Kelvin, 0.1 atm, 0 atm. There's like no movement now. I'm going to change this to kPa because that's a little bit more precise. Let's cool it down some more. Let's see if we can get it down to 0. Scientists have never actually gotten something to exactly 0 Kelvin. They got it to like 0.00001 Kelvin, but they've never actually got to 0. All right, so you can see at 0 Kelvin, we have no pressure. This is when molecules have no more motion. So this is fun to play around with. Try to understand what's going on, how volume, temperature, and pressure relate. It's all right here in this simulation for you. So now let's get to some calculations. We're going to do examples of each of these 3 gas laws that we did. So Boyle's law, remember, is P1 V1 equals P2 V2. I'm going to show you an easy way to remember these a little later. So it's basically plugging numbers in. These are typically easy problems. So let's see what we have here. A flexible container has a pressure of 100 kPa and a volume of 15 liters. So 100 kPa is the first pressure. It has a volume of 15 liters. There's P1 V1 equals P2 V2. What would be the new volume? So that's what we're solving for, is V2, if the pressure was reduced to 50 kPa. Okay, so you do the math. You solve for the V2. Remember, divide by the side that you're trying to find, so these cancel out. So 100 times 15 divided by 50, and that makes total sense, because look what happens. We went from having something that's 100 kPa to 15 liters. We cut the pressure in half. We went from 100 to 50. So what would you expect the volume to do? Because these are inversely proportional. As one goes up, the other goes down. If the pressure dropped by half, the volume's going to increase by 2, which is why we got 30. All right, let's take a look at another one. A balloon has a pressure of 300 kPa and a volume of 600 liters. So there's your P1 V1, 300, 600 liters equals P2 V2. What would be the new pressure? This time we're solving for pressure. And the volume increases to 900 liters. Okay, solve for pressure. Divide by P2, divide by 900 on both sides. Let's cancel out. 300 times 600 divided by 900 comes out to 200. And this was in kPa, so the units stay the same. Okay. Pretty simple. Just plugging in numbers to our formula. You just have to remember what the formulas are. All right, let's look at Charles' law. Charles' law is volume and temperature. V1 over T1 equals V2 over T2. So your question is only going to have volume and temperature in here. So container has a temperature of 300 Kelvin and a volume of 15 liters. So that's our 1. So temperature goes on the bottom, 15 liters. Okay, V over T. What would be the new volume? That's up here, V2, if the temperature was reduced to 150. All right, this is an equal sign, so we're doing crisscross multiplying here. We're doing this. All right, so let's just clean this up here. So we have 300 V equals 15 times 150. All right, divide both sides by 300. 15 times 150 divided by 300 comes out to 7.5. This is volume, so we're in liters. There's our answer. So look what happens here. Make sure your answers make sense. If your temperature went from 300 to 150, Charles' law is a proportional equation. As one goes up, the other goes up, one goes down, the other goes down. They do the same thing. So if this is going down by half, your volume is going to drop in half. So 15 is going to go to 7.5. Let's try this one. A balloon has a temperature of 100 Kelvin and a volume of 500 liters. So let's plug in our numbers. Our 100 Kelvin temperature is on the bottom. So we're going to put 100 in. Volume of 500 liters up top. What would be the new temperature, that's down here, if the volume increases to 1500? Okay, so I mean, without even thinking about it, it's going from 500 to 1500. we know this is proportional, so this is going up by a factor of 3. So our temperature should also go up by a factor of 3. So we should get an answer of 300 here. But let's do the math because it's not always so obvious. You're not always going to have nice, easy numbers. You know, you can see how this is a factor of 3. It's not always going to be that way. So let's just do the math. It's crisscrossing like this. So we're going to have 500T equals 100 times 1500. Divide both sides by 500. T equals 100 times 1500 divided by 500. And magically we get 300, and this is in Kelvin. Okay, these questions have been given you Kelvin temperatures already, so there's no need to do any conversions. If these were given to you in Celsius, remember you have to add 273. You have to plug them into this formula as a Kelvin temperature. You can't do the conversion afterwards. You have to do it before you do the math. And let's finally do Gay-Lussac's law. Gay-Lussac is pressure and temperature. P1 over T1 equals P2 over T2. All right, so let's just start plugging in numbers. The container has a temperature of 300 Kelvin. That goes on the bottom with a pressure of 3.5 atm. This time our pressure is in atm. Doesn't matter. We don't have to change anything. Just leave it alone. What would be the new pressure? Pressure's up top. If the temperature was reduced to 200. All right, so right away you should be thinking this is also a proportional relationship. As one goes up, the other goes up. As one goes down, the other goes down. So here our temperature is going down. So our pressure should also be coming down. We should get a number less than 3.5. So let's do the crisscross math here. We have 300 P equals 3.5 times 200. Okay, divide by the side where your unknown is. P equals 3.5 times 200 times divided by 300. And we come up with 2.33. This is ATM because we started with ATM up top. There we go, and that makes sense. It went from 3.5 to 2.3. It's about what it should do if the temperature went from 300 to 200. And let's try another one. We have a balloon with a temperature of 100 Kelvin with a pressure of 5 atm. Remember, P over T. What would be the new temperature if our pressure increased to 7.5? So this time our pressure increase, we should see an increase in temperature. Let's do the math. Crisscross, multiply. 5T equals 100 times 7.5. Divide both sides by 5. Our temperature is going to be 100 times 7.5 divided by 5. Comes out to 150 Kelvin. Okay, so our pressure went up, our temperature went up. Went from 100 and went to 150. Okay, and finally, there's something called the combined gas law. This combines all three of the formulas. PV over T equals PV over T. So one of the ways I remember this, if you just know this equation, you can derive the other three. And what ends up happening is just do this. So you have PV over T. So we have Boyles, we have Charles, we have Gay-Lussac. So alphabetically, BCG, start at the top and go around like a clock. PV is Boyles Law. That's the first one. B is the first one in the alphabet. Keep going around the clock. VT is Charles' Law. And keep going. PT is Gay-Lussac. This is an easy way to remember just by using the combined gas law, all three of the other laws. All right, so here we go. A container has an initial pressure of 5 atm, a volume of 20 liters at 300 Kelvin. So there's our P, V, and T1. So let's plug those in. 5, here's our P, a volume of 20. Just make sure you're putting them in the right spot. Temperature of 300. All right, what is the new volume? So we're looking for this over here, some volume. If the pressure goes to 10, make sure you're putting these in the right spot. PV over T. There you go. So you just have to solve for volume. You could do this however you want to do it. Again, it's crisscross, so I'll just do it this way. Let's go 400 times 5 times 20 equals 300 times 10 times V. Let's clean this up a little bit. 400 times 5 times 20. This is 40,000 equals 3,000 V. Divide both sides by 3,000. Just be careful doing these combined gas laws because the numbers can kind of get sloppy and kind of go crazy. So 40,000 divided by 3,000, we have a volume of 13.3, and this is in liters because that was liters up top. There you go. These are kind of harder to guess at because you got a lot of things going on here. You have the pressure is increasing, you have the temperature increasing. All right, in this case, the volume actually ended up dropping a little bit. All right, there we go, gas laws. This is part 1.